Watch the complete playlist on the app Pions. Download the app now.
So question number 1 says a slab of material of dielectric constant K has the same area as the plates of a parallel plate capacitor but has a thickness d by 2, where d is the separation between the plates. Find the expression of the capacitance when the slab is inserted between the plates. So let me first draw a rough parallel plate capacitor. So let's say this is our parallel plate capacitor and we are inserting a slab of material having dielectric constant K, which has the same area as the plates and thickness d by 2. So it will be d by 2. If this is d, the thickness here is d by 2. But area, as you can see, this part is same. Area is same, right? Find the expression for capacitance, okay, when the slab is inserted. And what's the dielectric constant of this slab? K. So first what we will do here is, first we will write the capacitance value without any dielectric slab. So what's the capacitance value without, okay, capacitance without dielectric slab. Now that is how much? That is C naught, which is epsilon naught A by D, where A is the area of the plates, epsilon naught permittivity of free space, and D is the separation between the plates, right? Now what we will do, now since we have inserted this, okay, because of this, what will happen? The electric field across this dielectric will change. It will get polarized, right? So what is the new electric field developed across this part, across this slab? E by or E naught by K. What is, sir, E naught? E naught was the electric field when there was no dielectric, when it was free space, right? It was E naught. And what was the value of E naught, if you remember? Sir, E naught in free was here sigma by epsilon naught, okay, in between the plates. So that we have done in theory, that electric field in between the plates of the capacitor is sigma by epsilon naught, in case if you don't know. And this E naught changes when you introduce a dielectric. Now this will change only in the region where we have the dielectric, right? If you don't have dielectric in the region, so there won't be any electric field change. So here in this region, let me write here, in this region, it will be E naught only. And there it will be how much? E naught by K. This is our electric field. I hope this is clear. Great. So because the electric field changed, there will be potential change. What will be the potential across the dielectric? Let's call it as V1. V1 is the potential across the dielectric and V2 is the potential in the free space. So the net voltage and the net potential in between the capacitor will be V equal to V1 plus V2, correct? Sir, why you are adding them? Because of the superposition principle. The total voltage will be the sum of individual voltages or potentials, right? So what is V1? Sir, V1 here is electric field E naught by K into that distance along which the electric field is there. So electric field into distance d by 2. Let me remind you, electric field into distance is nothing but voltage or potential difference, right? Plus, what is V2? V2 is electric field E naught into distance. What is the distance over that? If this is d by 2, the remaining distance will be also d by 2. This will be our V2. Again, I am repeating this step. The total potential between the two plates of the capacitor will be the sum of voltages V1 and V2. What is V1? The potential developed because of the presence of dielectric. And V2 is the voltage developed because of free space. So V1 will be electric field across the dielectric, which is E naught by K, into distance across the dielectric d by 2, and E naught plus into E naught by d by 2, that is the free space. Okay, great. Now what you will do? Let's substitute the value of E naught. Let me remind you once again, electric field E naught is nothing but sigma by epsilon naught. So sigma by epsilon naught d by 2 plus sigma by epsilon naught d by 2. Now what we will do? We will take common. You can see that sigma by epsilon d by 2 is common in both of them. So here we left with 1 by k and here we left with 1. In case if you are confused how to take common, let's multiply this sigma d by epsilon naught into 2, With the first term, you will get this, and multiply it with the second term, you will get the previous expression. Correct? Or you can write it as, let me take it to the next page. Okay, so the next one is here. So our potential will be sigma d by 2 epsilon naught into 1 by k plus 1. Correct? Let's go back. Sigma d by epsilon naught to 1 by k plus 1. Correct. Now, if this is the voltage developed between the plates of the capacitor, can we find the capacitance? Before we go to capacitance, let's write further some changes here. Sigma is nothing but surface charge density from first chapter. And what is surface charge density? Charge upon area. So 2 epsilon naught A, d goes up, and this will be 1 plus k whole divided by k. I hope this is clear. This is our voltage. Now fine. Now we can find the new capacitance. The new capacitance will be C dash, that will be equals to the C equals to what? Q upon V. So let's divide charge upon V. So what is V? V is, let me substitute here, it will be Q upon QD into 1 plus K will go in the denominator, and the remaining part will go in the numerator. So into 2 epsilon naught A into K. Let me repeat again. I substituted this V over here. And when you substitute that, what will happen? This will become QD 1 plus K 2 epsilon naught AK. Q and Q cancels. Now let's rewrite this expression. Epsilon naught A upon D into 2K by 1 plus K. Sir, what is epsilon naught A by D? It was the previous capacitance when there was no dielectric slab. So C dash will be equals to C naught 2K upon 1 plus K. Done. This is how our capacitance will change when you add a dielectric of thickness D by 2 in between the two plates, where K is the dielectric constant. Clear? So what you need to know before you uh, solve such problems, you should go through the derivations of parallel plate capacitor, like electric field, how the polarization takes place in case of dielectric, okay, and how the electric field changes because of that. What is dielectric constant? These are the prerequisites for these questions. Let's move to question number 2. Our question number 2 says, in a parallel plate capacitor, the capacitance increases from 4 microfarad. So let's say C initial capacitance was 4 microfarad 10 to the power minus 6 farad to 80 microfarad. This is CF, the final, that is 80 into 10 to the power minus 6 farad. On introducing a dielectric medium between the plates, what is the dielectric constant of the medium? So always remember, if you divide, because this is going to 80 microfarad once you add the dielectric. So CF upon CI must be equal to K, because we know the formula that always new capacitance will be K times the initial capacitance, right? So K will be C dash upon C naught. So let's divide CF, the final one, which is 80 into 10 to the power minus 6 whole divided by 4 into 10 to the power minus 6, which is equals to K. Cancel out this 20. That is our dielectric constant value. Let's move to question number 3. Question 3 says, a parallel plate capacitor with air between the plates has a capacitance 8 microfarad. So C here is 8 microfarad 10 to the power minus 6 farad. The separation between the plate is now reduced by half. So now previously the capacitance was, okay, at a distance D, let's say, the area of plates was A, let's say, and that time the capacitance is C, okay. Now the distance, the separation became half. So now we got D by 2. Let's read ahead what they said. The separation between the plate is now reduced by half, and the space between them is filled with a medium of dielectric constant 5. Okay, great. Now the dielectric constant is 5 here. This is completely filled here, okay. So calculate the value of capacitance of the capacitor in the second case. So what will be C dash? So C dash must be equal to KC. But be very careful with this C. Now this C is no more epsilon naught A by D, because previously it was epsilon naught A by D, right? Now this D is changed. So this will become K epsilon naught A upon D by 2. Now the distance become half. So let's take this 2 on the top, 2K times epsilon naught A by D, and put the values now. So this will be 2 into K. What's the K value? 5. And what's epsilon naught A by D? Look at this one. This is our previous capacitance, 8 microfarad, 10 to the power minus 6 farad. 5 twos are 10, 10 multiplied with 8, 80 microfarad. That's your new capacitance value for question number 3. Great. Let's move to question number 4. Question number 4 says an ebonite plate. Now you don't have to care about what it is because it's a dielectric. Okay, with a dielectric constant, K value here is how much? 3 and 6 millimeter thick. So thickness T is 6 millimeter. So let me write it as 6 into 10 to the power minus 3 meters is introduced between the parallel plate of a capacitor with the plate area A is equals to 2 into 10 to the power minus 2 meters square. This is the area. And the plate separation is D here is 0.01 meter. Now be very careful because this is quite important. Okay. This will clear our concept of parallel plate capacitor once again. So what we will do here is we will first draw a simple parallel plate capacitor here. The separation between them is D, between the plates, right? And area of each plate is A. Okay. Now they are saying that you are putting here a dielectric with some thickness T, correct? So this thickness is 6 millimeter, which we will take into account within a minute. So if this is T and this is D, what will be this? So D minus T, correct? Be very careful with this. Now what is D? Let's put the value. So value for D is 0.01. Okay, great. And what is T? Says T is how much? 6 millimeter. So it will be 0.006, correct? So what will be this gap? That will be 0.01 minus 0.06, right? I'm just for the timing, I'm not solving, I'm just keeping it like this, right? Okay. Again, I'm repeating, we have a dielectric which is placed across this distance and the remaining space is free, empty. Where there is a dielectric, the electric field will change? Yes. How it will change? Sir, it will change as E naught upon K, where K will be the dielectric constant of that. Clear? Now, if it is K is 0 or K is infinite, okay, in that case, the electric field will vary differently. So here, there is no dielectric. So here there will be simply electric field will be E naught because it is not there. Dielectric will polarize, and because it get polarized, the electric field changes across the dielectric, right? Great. So if these are the electric fields, we don't know what is the value of electric field, right? So don't worry about that thing. Okay. So let me take this as thickness T and let me take it as D minus T for the time being, so that at the end, when I will get a perfect relation, in that I will directly put it. Okay. So that you don't get confused, sir. We don't have electric field given in the question, and even the voltages are not given and other parameters not given. So don't worry about that thing. We will see that at the end. So in what section our dielectric is there? T, and empty space is D minus T. So in this across the ebonite plate, voltage V1 will be equals to how much? So electric E naught upon K into thickness T, right? Electric field into distance is our voltage. So across the ebonite plate, the voltage will be electric field into thickness T. Now, what is our, this is our across this one. Next is our in empty space. So V2 will be equals to electric field E naught into D minus T. Clear? Yes, because the electric field in empty space is E naught and the separation is D minus T. I hope this is clear. What will be the net potential? The total potential will be V, which is equals to V1 plus V2. If the net voltage is V1 plus V2, V1 is E naught upon K into thickness T plus E naught into D minus T. And what is the electric field between any parallel plate capacitor? Let me remind you, it is nothing but sigma by epsilon naught. What is sigma? Surface charge density, which is charge per unit area. We will substitute now that in this. So this will become, one second, this will become, let me remove this here and let me solve it here only. So this expression will become V will be equals to E naught, which is sigma upon epsilon naught K T plus sigma upon epsilon naught D minus T. And what is sigma? Just now I told you charge upon area. Charge upon area. So what will be the new capacitance? Charge upon this new voltage V. Before we write this voltage, let me take common here Q by epsilon naught A. So that here I left with T upon K plus D minus T. Now let's substitute this value. It will be Q upon, what is this? Q epsilon naught A goes up. And here we left with thickness T by K plus D minus T. Let's cancel this Q with Q. So we left with epsilon naught 8.854. 8.854 into 10 to the power minus 12. Area 2 into 10 to the power minus 2 whole divided by thickness. Thickness is 6 millimeter. K value is 3 plus D 0.01 10 to the power minus 2 minus T 6 into 10 to the power minus 3. Let's simplify it further. Okay. And over here on the left hand side. So let me just take roughly 8.854 as 9 into 10 to the power minus 12. Correct. Into and 10 to the power minus 12 and 10 to the power minus 2, 10 to the power minus 14 into 2 whole divided by 6 by 3, 2 into 10 to the power minus 3 plus 10 to the power minus 2 minus 6 into 10 to the power minus 3. Correct? Now this 2 into 10 to the power minus 3 and 6 into 10 raised to minus 3, it becomes minus 4 into 10 to the power minus 3. Let me put it here. This will be our capacitance. Okay. Now, before that, let me just take 10 to the power minus 2 common out from the denominator. So 9 to the 18 into 10 to the power minus 14 whole divided by 10 to the power minus 2 taking common. This will give me 1 minus 4 into 10 to the power minus 1, right? So that is 0.4. Let me repeat again. When you take 10 to the power minus 2 common out, you left with 1 minus 4 into 10 to the power minus 3, out of which 2 is already taken out. So 10 to the power minus 1. And 4 into 10 to the power minus 1 is 0.4. 1 minus 0.4, that is nothing but 0.6. So let's multiply here with 0.6. Let's remove this. 1 of the 10 goes up. 6 threes are. So 3, approximately 3 into 10 to the power minus 2 and 1, 3, and that will be minus 11 farad. That will be the new capacitance of this capacitor because of the dielectric. So let's move to question number 5. Question number 5 says a slab of material of dielectric constant K has the same area as the plates of the parallel plate capacitor but has a thickness 3D by 4. So let's draw this. Here this is our parallel plate capacitor. Let's put here a dielectric, and this is of thickness 3D by 4. If the total separation is D and this part is 3D by 4, how much is this part, empty space? D by 4. Sir, how you got D by 4? You can subtract D minus 3D by 4. You will get D by 4. Or if you add both of them, you will get D. Right? Where D is the separation between the plates. How is the capacitance changed when the slab is inserted here? So if this is 3D by 4 and this is D by 4, in place where you have placed this dielectric slab, there will be change in electric field. Once again, I am repeating this. So electric field changes E naught by K, where K is the dielectric constant of this. And here the electric field still remains E naught. Why? Because there is no dielectric here. So what will be the voltage across the dielectric? Sir, voltage across the dielectric will be V1. That will be electric field across the dielectric, which is E naught by K, into that separation, which is 3D by 4. Let me repeat again. The voltage is nothing but electric field into distance. So electric field across this dielectric is E naught by K, and this distance is 3D by 4, right? Now what's your voltage V2? V2 is the voltage across this empty space across the capacitor, and the electric field across that empty space is E naught into the separation is D by 4. So net voltage will be V, which is equals to V1 plus V2 by superposition principle. Let's add both of them. So it will become E naught by K into 3D by 4 plus E naught into D by 4, right? Now what's our electric field for a parallel plate capacitor in between the two plates? So sigma by epsilon naught. Let me repeat. Sigma by epsilon naught is the electric field in between the plates of the capacitor. How we got this? Go through the derivations. Clear? So this will be our sigma by epsilon naught. In place of electric field I am putting here. E naught is sigma by epsilon naught. Clear? So this is our voltage. Now voltage is, if this is our voltage, what we will do? Now we will first we will put the value of sigma. So let me put here from first chapter, sigma is nothing but surface charge density. So this will be Q by epsilon naught K into A. Q by A is sigma into 3D by 4 plus Q by epsilon naught A and D by 4. Q by A is sigma. Now what is common between both? Let's see. Sir, Q is there in both the terms in the numerator. D is also there in the numerator. Epsilon naught is there in both them. A is there in both of them. 4 is there in both of them. So what we left with here? 3 by K plus 1. Now this can be written here as QD upon 4 epsilon naught A K plus 3 plus K upon K. Correct? This is our voltage. If this is the voltage across this capacitor, what will be the capacitance? Sir, capacitance will be simply charge upon voltage. So what is our voltage? Q upon voltage. Q, D and 3 plus K. Remaining one will go up 4 epsilon naught A K. Let's remove this with this. So we left with capacitance value C, which will be equals to epsilon naught A by D 4K upon K plus 3. Now what is epsilon naught A by D? So it was the initial capacitance of the capacitor C naught. If you want to write, or you can leave it as the previous one. So C naught is the initial capacitance, which is without the dielectric slab, epsilon naught A by D. Because of the slab, it became this one. Done. This is our correct answer. Great. Let's move to question number 6. Question number 6 says a slab of material of dielectric constant K has the same area as the plate area, okay, of a parallel plate capacitor, but has thickness D by 2, where D is the separation between. Okay. Find the expression for the capacitance. Now by now, I hope we have done so many problems, so it will be very easy for us now. So this is our dielectric. With the dielectric slab, how much thickness? D by 2. So if this is D by 2, empty space will be of D by 2. What will be our electric field here? E naught by K. And what is our electric field over here? E naught. So what is our first task? To find the voltage. So V1 will be the potential across the region where the dielectric is there. So that will be our electric field in that region times the separation D by 2. What is V2? That will be our electric field E naught into D by 2. I hope this is clear. Now net voltage will be V will be equals to V1 plus V2. And V1 is nothing but E naught D upon 2K plus E naught D by 2. What is our electric field E naught? So sigma by epsilon naught D upon 2K plus sigma by epsilon naught D by 2. This is our voltage V. Correct? Now what we will do? Now we will write it as V equals sigma charge upon area d by 2k plus charge upon area d by 2. Let's take common out. Q d upon epsilon naught A. Okay. And 2 is also common. So 1 by k plus 1. I hope this is clear. So let's write it in the next one. V equals to Q d by epsilon naught A into 2. Let me check what we have written. 1 by k plus 1. So that I am taking LCM. So 1 plus k upon k. This is our voltage. If this is our voltage, what is our new capacitance? C dash, which will be equal to charge upon voltage V. So what is our voltage? Q upon QD into 1 plus K epsilon naught A into 2K. Q cancels with Q. So C dash will be epsilon naught A upon D 2K upon K plus 1. What is epsilon naught A by D? The previous capacitance when there was only air in between. Done. This is our complete answer to this question. Done. Let's see the next one. Question 7. Two capacitors having capacitance of 5 microfarad when connected in parallel and 1.2 microfarad when connected in series. Calculate their capacitance. Okay, so basically you have two capacitors. Let's call them C1 and C2. Okay, once they are connected in series, once they are connected in parallel. It's not given that they are equal. So let's call them as C1 and C2. Okay, two capacitors have a capacitance of 5 microfarad when they are connected in parallel. So this is C1 and C2. And they have equivalent in this case how much? 5. So C1 plus C2 directly, that is equals to 5 microfarad. Sir, you have to convert that microfarad. No need of conversion. That will confuse you because anyway C1 and C2 will be in microfarad. Then only their sum is microfarad, right? And connected in parallel and 1.2 in series. So here 1 by C1 plus 1 by C2, that is equals to how much? 1.2. Clear? This is equation 1 and this is equation 2. We have to solve them simultaneously to get the value of C1 and C2. Correct? So let's substitute 1 by C1. C1 will be how much? From 1 and 2. Let me write here first. From 1 and 2. 1 and 2. C1 will be nothing but 5 minus C2. So when you substitute, it will be 1 upon 5 minus C2 plus 1 upon C2 will be equals to 1.2. Let's cross multiply. It will be C2 plus 5 minus C2 whole divided by C2 into 5 minus C2. And that is equals to 1.2. Correct. Now C2 cancels with C2 and we left with 5, which is equals to 1.2 into C2 into 5 minus C2. Let's remove this point and make it upon 10 so that our calculations becomes quite easy. So 50 is equals to 12 C2 into 5 minus C2. Correct. Okay. So let me write this equation here. It will be 50 is equals to 12 C2 into how much it is? 5 minus C2. 5 minus C2. Correct. Now let's simplify further. 50 is equals to 12 is a 60 C2 minus 12 C2 square. Be very careful. 12 C2 square. Okay. Now next is this will be 12 C2 square is equals to minus 60 C2 plus 50 is equals to 0. I took this 12 C2 on the left hand side, 60 C2 and plus 50 equal to 0. Now let's is there anything which can cancel out? Let's divide the whole equation with 4. It will cancel out. No, 6 2. Let's divide the whole equation. 2 6 2 30s and 2 25s equal to 0. Now let's simplify further. So 25 into 6. Okay, you can either use alpha and beta also if you want to. Okay, by using that plus minus. Okay, that minus b plus minus root under b square minus 4ac upon 2a. You can use that formula to directly find the solutions. or you can do middle term splitting. So let me just try middle term directly. If we can find 6 5s are 30 and 150 we got. Okay, so 150, the solutions can be, or we can use alpha beta. That will be much faster in this case because numbers are huge, right? So alpha will be equals to minus b, which is 30, plus root under b square, which is 900, minus 4ac, 4 6 or 425 is 100, 100 into 6, 600, whole divided by twice of a, which is 12. So this will be 30 plus root under 900, 300, whole divided by 12, correct? So, and this will be 30 plus 10 root 3 whole divided by 12. Okay, so that is alpha, and you can divide this whole thing with your 2 2 15s, 2 5s, and 2 6, correct? Up and down I cancelled. So if this is one of the possible value of C2, then beta will be equals to how much? 15 minus 5 root 3 upon 6, correct? So these are the values of alpha and beta. Now if these are the two values of C2, we can find the value of C1. C1 will be 5 minus C2, right? So C1 will be simply 5 minus, we can subtract any both of the values, you will get 15 plus 5 root 3 whole divided by 6. So this will be 30 minus 15. 15, when you cross multiply, 5 6 is 30, 30 minus 15, 15 minus 5 root 3 upon 6. This is our C1. And when you put C2, C1 another value. This is the first value of C1. When you put alpha, when you put beta, then the C1 value will be, that will be how much? 5 minus 15 minus 5 root 3 upon 6. So that will give us 15 plus 5 root 3 upon 6. So these are the two possible values of C1 and C2 for this combination to take place. Great. So I hope this is clear. Let's move to next one. That is question number 8. Question number 8 says, calculate the work done to associate the four charges at the corners of a square with side length r. Now what students do blindly, okay, because they don't practice, they directly attend the lecture and then they forget. So what they usually do is they'll say that, see, this sir, we have four charges. We can directly say that U1, we can directly find the potential energy between first and the second charge, second and the third charge, third and the fourth charge, and simply add all the potential energies, which we usually do for potentials, right? So what you will do, sir, K Q1 Q2 by R over formula for potential energy is, since it's a scalar quantity, it will be 1 by 4 pi epsilon naught charge Q1 Q2 upon the separation between them, right? And sir, first find between BC, then find CD, then AD and AB, and then it's done. No, it's not done like that. Be very careful. Formula is this, but the way we solve it for potential energy, that's different way. Okay, so you have to be very careful while dealing with potential energy. So right, so what we have to do for potential energy, basically what you will do is, you will first, let's start from any one. You can choose any one of them, and let me start it from let's say A. So I'm putting my first charge at A, okay, here. And what is the magnitude of the charge as per the diagram? Minus 2q. So to put this first charge at this place, you have to do some work? No. Why you don't have to do work? Because there is no one to influence this charge, right? If you are sitting alone in a room, you can't talk with anyone. Okay. Now don't say, sir, I can talk with myself. Okay. Now that's another issue. So here, if you are sitting alone in a room, you are not interacting with anyone. So this charge is not interacting with anyone. So U1 will be equals to 0. Potential energy required to put this charge at this point where there is no other charge will be 0. Now let's go to B. So if I place the second charge B at a distance of r, as per the question, the square has a side length r, and this is our Q. Now when you place the second charge, you have to do some work either against this first charge or in favor of that charge, depending on the signs of the charge, right? If this is positive and that is negative, they both are attracting. If that is both are negative, they will repel, or both are positive, they will repel, right? So if you're placing here, you are doing some work. Now U2 is the amount of work you have to do to place the second charge at that position, and that will be 1 by 4 pi epsilon naught Q1 Q2. Let me remind you once again, potential energy is a scalar quantity, so negative sign is to be taken here in this chapter. whole divided by r. This is the potential energy required to place this second charge at that point. Now, if you are placing the third charge at this place, this minus q, this is the third person entering the room. So this person can interact with this person as well as this person. Now, when I am saying interaction, I am not saying that they will talk or they'll fight or they'll do whatever attractive, repulsive, whatever is the interaction, but this will interact with this as well as this. So when this is interacting with this, what is the separation here? R. So U3 is the amount of potential energy required to place the third charge at that point. And when you're placing it there, it will be 1 upon 4 pi epsilon naught, the charge first one, the charge second one, whole divided by r. This is the interaction of this with that. Plus, be very careful, plus the potential energy required to place these two charges. The interaction between these two charges. And what is this gap? Sir, if this is r and that is r, using Pythagoras theorem, this will be root 2r, the separation or this diagonal. So separation between C and A is root 2r. Why root 2r? You can use Pythagoras theorem. If this is r and this is r, use Pythagoras theorem, hypotenuse square equal to perpendicular square plus base square. You will get eventually root 2r. And now that will be 1 by 4 pi epsilon naught. First charge, second charge, whole divided by root 2r. You have to be very careful. Now, majority of people go wrong here only. That's why I am solving. Because they directly, when they write, this factor of root 2r doesn't arrive. Because everywhere they take this as r, this as r, this as r, this as r. And they directly write it as r, r, r. Root 2r will come only if you are placing the charges one by one and then only you are solving, then you will get. Let's place the fourth charge over here. Now the fourth person enters the room. Now this person will interact with all the three, maybe attractive, maybe repulsive, depending on the signs. But when it is entering, it is interacting. And you have to do some work when you are placing it against all three. So potential energy required to place the fourth charge will be interaction of this charge with the A charge. Let's put it here, 1 by 4 pi epsilon naught. 2q is the charge which we are placing, minus 2q it is influencing upon the separation between both, which is r. Then interaction of this with the B charge. So this is again diagonal, right? Square diagonals equal root 2r. So this will be 1 by 4 pi epsilon naught. The first charge, 2q, interacting with q, whole divided by root 2r. Finally, interaction with the third charge, which is C. So it will be 1 by 4 pi epsilon naught. First charge, 2q. Second charge, minus q, whole divided by how much? R. So which one is the correct answer? So you have to add all of them. Okay. So the total potential energy required to assemble all of them together will be U1 plus U2 plus U3 plus U4. U4, sorry. So let's put here U1. What's our U1? Sir, 0. Be very careful with the signs. Now minus into this will be minus 2q square upon 4 pi epsilon naught r. That is U2. U3, q and q, minus q square upon 4 pi epsilon naught r. Minus minus plus 2q square upon 4 pi epsilon naught root 2r. Done with the third one, U3. Fourth one, U4. Minus minus 4q square upon 4 pi epsilon naught r plus 2q square upon how much? 4 pi epsilon naught root 2r. And how much here? Minus 2q square upon 4 pi epsilon naught r. Correct? So these are our parameters. Now let's simplify it further. So this, okay, minus 2q square and minus 2q square. Which one? This one and this one. So 2 and 2 is, because they are same. Even r here and 2q square. Minus 2 and minus 2, minus 4q square by. So let me write here. The final energy is minus 4q square by 4 pi epsilon naught r. Okay, how I got 4q? Again, I am repeating. See, this is one apple. plus 1 apple, it will become 2 apples. So multiply this parameter with 2. So you will get minus 4q square. Correct? Next, let's move to any other r parameter. Yes, here it is. So this will be minus q square and minus 4q square. How much it is? Minus q square and minus 4q square. Minus 5q square. Let me write here minus 5q square upon 4 pi epsilon naught r. Correct? Let's move ahead. Then we left with this root 2 parameters, like root 2 are here and root 2 are here. So 2 and 2, 4. So here 2 and this 2, 4. 4q square by 4q square by 4 pi epsilon naught root 2r. Correct? Great. Now 5 and 4 minus minus plus. So minus 9q square upon 4 pi epsilon naught r plus 4q square upon 4 pi epsilon naught root 2r. Now what we'll do? Sir, now you can take q square, which is common in both, 4 pi epsilon naught r, which is common, and what we left with minus 9 by 4 plus 4 by root 2. You can leave it like this. This is our total potential energy to assemble group of these group of 4 charges at the corners.
Watch the complete playlist on the app Pions. Download the app now.